Good afternoon, everyone. This is lecture 15 E512 CMOS Analog IC Design, September 30, 2023. I would recommend try to understand the course rather than practicing. Because when I used to study, I used to see that those people who are you know mugging up the whole book, they are getting more marks than those who are understanding. I'm giving you plenty of time to solve that. Answer is very simple. The only thing is to reach that, to understand that, you require to understand analog. This is what I'm expecting from you people. If you don't understand, then there is no point in practicing questions. For practicing, maybe you can use Behzad-Razavi. Its solution is already available, right? Alan Holberg, that solution is, by the way, Behzad-Razavi himself solved that. That solution has been given to you. It is by Behzad-Razavi only. With his own handwriting. That is the thing, you got it, right? Same way Alan Holberg, so that's written in latex, so that is there. What else? Willie Sampson, right? But question paper is not copied from anywhere. Okay. Okay, so we are talking about current mirror or the current source, where our two agendas are there. Z out has to be as large as infinity and V out has to be as minimum as 0, or you can call this one as V min also. We also learn that if you want to improve output impedance, you can make that cascode. And you can find out the impedances, right? So what is the impedance looking from here? Z out. This does not require, like, we are doing practicing only, right? In class. Come to class, you will practice everything. I believe you don't require to read anything else. Okay, what about V out? From here to here. 2 VDS plus VTH. And here it's VDS plus VTH. Here another VDS plus VTH. Right? So outer side you will be having like addition of these two minus 1 VTH lower. So that's 2 VDS plus VTH. Depending on technology and other things, VTH is changing. However, VDS we are trying to achieve more than 250 millivolt just to make sure that this transistor stays in saturation and gives the required value of the current or voltage or whatever you want, right? So this is what we studied, right? So there is no problem in this. Now let's go another configuration, which is very popular, known by the name of the scientist called Wilson current mirror, right? So he gave this topology. It is look-alike to cascode only. So if I am interested in R out, what will be the R out here? GM4, right? Right. So this is the R out. The only thing is here you are not getting too much gain in terms of R out. However, there is some gain actually, right? So that is there. What about V out? Let's find out and tell me. By the way, this particular topology is good for one reason, that you are having two feedbacks. So the current flowing from here is getting, mirrored over here. However, you just look at this particular topology, it is having two feedbacks. One feedback is from here. So on the basis of available voltage over here, the current will be mirrored over here, and on the basis of voltage over here, the current is getting mirrored over here. So after few loops of feedback, you are going to have nearly same current. So it is more stable and better current mirror topology. However, the output impedance is not so high as you had in a normal cascode. So that's the main difference. So you can see over here, so that two current feedbacks are there, kept it in a other side. So now tell me, what will be the V out? Two VDS. Okay. One answer is two VDS. If someone has something else, just let me know. Hint is like Abhishek is in right direction, that it has to be written in terms of VDS rather than writing in terms of VGS. Right? Is it correct or wrong?
So 2 VDS plus VTS.
Okay. How did you get this 2 VDS plus VTS?
Like we said, the downward is VDS plus VTS.
Okay. But it is VDS already, right? It is VDS. It is already VDS. VGS is equal to VDS, right? So drain to source voltage is actually changing the gate, right? Not other side. So that's what I was saying. Write it down in terms of VDS. So that was, and here VDS plus VTS, right? Yeah. Right. But if you are going this way, like there are, as I told you, it's in your hand that how you are designing it. If you're if you're going to keep this one VDS plus VTS, then also fine. Then also fine. But your answer is also correct. So it has two answers. It remains with you people as a designer, that do you want to keep this one as VDS plus VT, or you want to keep it only VDS, right? So you have to tune this. This is with respect to ground. So there might be two answers: two VDS plus VT or two VDS, right? So any one of them you can use it. Okay. So another topology. This is generally self-biased topology, right? It is also one of the, already I gave the answer here. So here, okay, I'll try to draw this again. So there are two branches are there. And what about this one? This must be, made a mistake. So all gates are shorted here, right? So if the current is IREF over here, then you want to have mirroring over here. This will have certain advantage. We'll see that. First of all, let's find out what is the output impedance, right? So that must be very easier, right? M1, 2, M3, this M4 and M5. So what is the output resistance over here? I haven't seen like so much, easily giving answer in the paper, the exam paper. People were writing all, I don't know how to say. People are not writing this answer very simple way. Some people have written, something, just, I don't know, with their brain, whatever they found out, or they wrote something from the book. I believe, not approximated or anyway. So this is one thing. Now find what is the value of voltage over here. Look at this. Try what answer you are seeing.
VDS minus VTH.
Just find out. I'm writing just VDS minus VTH. You try and find out. I think we are doing this just for one reason, that cascode is giving us good output resistance. However, V out is not very as per our expectation. We want to keep it as low as possible. So that is what we are trying to achieve over here. So in that case, how much will be the VDS, or sorry, V out? You find out from here to there and you write down. Same voltage will go there. You can start from left side if you want, because that is the main cause of all the voltages, and like from here you can start and you can write down if you wish, or if you want to assume somewhere else, you can do that. It's not easy. First time if you are doing, then it's not easy. You try. Keep some voltage over here. Still I am saying, this is, you are the designer, you are defining this. Still I am saying, you are the designer, you are defining this. Just I'll tell you one way. Let's go this way. My answer is wrong answer, but I'm telling you how to think. If I'm keeping here some voltage, let's say VDS or VDS plus VTH, let's assume that VDS plus VTH is over here, which is actually driving here. So from here to here, because this is with respect to ground, from here to here, as per my assumption, this becomes VDS plus VTH. Do you agree with this? Then output should be VDS. But single VDS, if it is single VDS, it's not good enough to make two transistors in saturation. One VDS is 250 millivolt. I need minimum 250 millivolt here and 250 millivolt here. Understand, by looking at this itself, you can say that 2 VDS is the minimum voltage, just to make sure that this transistor or these will be in saturation. Do you understand? So this is required to think this way also. So if you are going this way, then it's a wrong answer. Pragya. So now find out. So minimum voltage here required is VDS. VDS is required. In addition to that, something is coming because of this biasing. It might be some other value also. Or if you want to do it this way, that you keep this to as VDS, then how much voltage is required here? 2 VDS plus VTH, right? Then this is also 2 VDS plus VTH. If this is 2 VDS plus VTH, how much is this voltage then? You have to determine these voltages also and understand each one of the VDS has to be VDS or 250 millivolts. Here you give lots of voltage. Here you give 2 VDS plus VTH. If you are giving this here, then how much voltages are required at different transistors? Find out and tell me. You have to allocate the required budget of the voltage. Are you following or writing in hand? Gaurav? Gaurav कहाँ? You are Gaurav. Location बदल जाता है, like you used to sit there, right? So Gaurav, any answer for this one? Vishal is here. Vishal, what's the answer? It's very easy, not so difficult, right? always remember one gentleman, that's Kirchhoff. So use Kirchhoff's voltage law, Kirchhoff's current law, whatever you like, you just use it. As I told you, if you want to achieve 2 VDS here, I want to achieve 2 VDS because previous circuit was also giving me 2 VDS plus VTH as well as 2 VDS also, right? So I would say that if I can achieve here 2 VDS, then it's a good thing. Let's design it such a way that I am getting 2 VDS. Then what are the different voltages are required here and here? It is not always compulsion that you are going to tune with the voltages. Okay, I'll tell you that trick after this. Once you will, get the answer. So how much is the voltage here? If you got this this one is 2 VDS, then if this is 2 VDS plus VTH from here to here, and how to distribute that? You have to distribute it, right? This is also 2 VDS plus VTH, and this is also 2 VDS plus VTH, right? Rest of them, tell me what are the voltages here? 2 voltages I am looking for. How do you think? I just want to understand. Yeah. What's your name? Adarsh.
Ajay.
Ajay. So Ajay, what voltage you are going to keep here? Let's say. Let's start from here. If you keep here 2 VDS. Okay, let's try with different color. I'm keeping whatever you are thinking. If 2 VDS is here, then how much voltage is here? Okay, 2 VDS plus VTH. Okay. So if this is 2 VDS plus VTH, understand? Drain to source. So what is the VDS value of M2? VTH. Only VTH, right? Because if I am looking from here to here, this point, it is 2 VDS plus VTH, amongst which 2 VDS is already here. So I have to keep VTH only here, which may not be sufficient to make this transistor in saturation. That is the meaning of that. So I'm just trying to teach you how to think. Okay, just go ahead and tell me how much voltage is required just to make sure that both the transistors are in saturation. Look, minimum required voltage is actually VDS. Minimum required voltage is VDS. I'm referring VDS set as VDS, by the way, which is 250 millivolt or more than that. Aman, are you following? So, batao, what is the voltage? Am I going fast or going fine? Okay. There is no unique answer, by the way. Okay, there is no unique answer. One of the answer I'll show you, but that's not the unique answer. As I told you, minimum voltage required is VDS. You keep that. You can redistribute it. What's the big thing about it? One of them you can keep it VDS plus VTH and another as VDS, right? Anywhere, wherever you like. One of them maybe VDS plus VTH, one of them is only VDS, right? Then it will work. Then it will give you the required voltage. But as I told you, this is not the unique solution. There are many possible ways you can achieve the required voltage. One of the solution is, somebody has told 2 VDS over here, right? If you want to keep 2 VDS, then you can make this depleted mode also and keeping VDS. That is also possible, right? It is not shown, but there are multiple answers are there. Multiple things you can make them as depleted mode, and then you can run it, right? So Like, okay, as I already told you about this, right? What is the mistake I'm saying? Okay, if this is like another solution is if this is VDS plus VTH, and if this is VDS, then and then it's 2 VDS plus VTH, so output is 2 VDS. In that case, this becomes VDS plus VTH. So if one of them is VDS, another is VTH, in that case, that transistor has to be in depletion mode, or maybe other way around. So as I told you, it's you people who are designing this, so depending on you, right? But how to achieve these voltages? What do you think? When you are going to design, let's say, such kind of current mirrors in laboratory, so how to achieve these voltages? If it is not coming, then what are you going to do? When you design it, like keeping W by L, whatever you W by L kept it over here, you made some. Hmm?
That will need not to be changed.
What?
W by L.
W by L I am not changing. I am not changing W by L. But always you can change the ratio,
Yes.
right? It has to be uniformly changed, through which you can design it. It is like if there is a big transistor whose width is bigger, length is bigger, so then it requires more voltage to push it, right? It's like a door, one side you are standing. If there is one guy, it's a single W. If there are two guys, three guys, then more pressure is required from other side. So if you want to increase this voltage, accordingly you have to change the ratio. You have to take up and down, but make sure that unit size remains same. If it is not same, then it's create a problem, right? Because it's all about the matching over the PVT corner. Maybe after maybe 1 or 2 labs, we will do that. That we will, instead of working at typical corner, let's change it to slow corner, or maybe fast corner, and see what is happening. Maybe the results might be very surprisingly. You will see that most of the transistors are going out of the saturation and giving you lots of problems. But anyway, this is what I wanted to convey over here. To achieve 2 VDS, you can do this one. You can achieve more also, 2 VDS plus VTH also. If you are designing badly, that's why designer has to be very wise. Without practice, understanding, I would say that, right? So any current mirror I am giving, then can you solve that? As I'm saying, there is no unique answer, but the one thing you have to follow, that all the transistors have to be in saturation, right? Then and then that will give you the required V out, right? Okay. There is one more technique which is also known as self-biased cascode current mirror. So what is the advantage in this? Like comparing to this one, what could be the advantage over here? Going in self-biased mode. It is exactly same topology. I'm just removing this part, right? I'm just removing that and make sure that it does not require the voltage. It's coming from internal circuitry itself. It has one branch lesser than what we had, right? You can see there were 3 branches. If supply voltage is equal to, let's say, 1 volt, if IREF is equal to, let's assume that 10 microampere, and each one of them is also same IREF, if I'm, or let's say, if I'm doing this one, the total current flowing through this circuit is 40 micro multiplied with supply voltage of 1 volt. So the power consumption is 40 microwatt, right, in this circuit. However, in this case, if from here, if I'm expecting 10 micro, other side 20 micro, the power consumption is 30 microwatt, right? That's why we are actually removing one branch, and we are considering this as a master one. Everything is exactly same later on. Like there is no change in terms of R out. R out is very simple. If it is M3 and M4, again I'm asking, Aman, what do you think? R out? बताओ जल्दी. GM3, RO3,
GM,
RO4. Okay. So it's very simple. V out is already written over here. So tell me which are the voltages. Okay. Some voltages are already kept over here. So if this is VDS plus VTH, then one of the transistor has to be in depleted mode in that case, right? Or you can distribute other way around where you can have the required voltage accordingly. If this is 2 VDS plus VTH, means from this point to this point, you have to, you can do this one. Do not consider this one. We can do this one, right? If this is 2 VDS plus VTH, as per the case KVL, I can allot here VTH, I can allot here VDS, and I can allot here VDS. It makes 2 VDS plus VTH, right? And same coming here, so this is going to be 2 VDS then, right? And of course, then it will be only VTH. Right? So accordingly, you can design here and there, right? And you can achieve the required voltage just to make sure that across each transistor, wherever I am keeping yellow, VDS has to be more than 250 millivolt. This is the Guru Mantra everywhere used. If you want to design a good analog circuits, right, it will work. Okay. So again, I am saying this is from the experience. Do not tell any guy who is in front of you for taking your interview. This number does not have any proof. Okay. This is just to design it for efficiently. Right? When you are going to design it, you will understand. The way, yeah. I believe that guy will also understand. When you're talking to him, he will understand, but he does not expect this answer from you. Anyway, so as we know that we wanted to have current source which has only two things, Z out as infinity and V out as V min. So we could have made cascode as a good option. However, there was some problem in terms of V out, which was not coming as really, 0. In the normal one, we were seeing VDS, but with cascode, we were seeing 2 VDS plus VTH, even 3 VDS plus 2 VTH, and so on and so forth, if you are stacking more and more transistors. So, we invented two different topology, or actually three different topology. One is called Wilson, which is having feedback. Feedback is very good. There is no problem in terms of stability. Maybe in future, again, when we will touch this, you will understand pole zero, all these things can be, tuned properly. So that is also the advantage of Wilson, and it has a better stability. However, in case of other, by the way, in this case, you are achieving good Z out, actually not as good as normal cascode. It is better, a little bit lower than that one. V out is as bad as other people, right? So that was the problem. In terms of another where we had three branches, right? We achieved good Z out and try to reduce V out by 2 VDS. Other one, we call it self-biased circuit, where we do not have three branches, so we are reducing power with V out equal to 2 VDS, and all of them has good Z out, means GM RO square, right? If every transistor are perfectly matched and every RO and everything is correct, so GM RO square, or it gives you GM n RO n plus 1, right? This is what you can get as you are adding the number of stages, right? Okay. So now, how to improve? Like, we are more greedy. We understand cascode is one technique through which you can get good Z out, and you can have required V out also. V out is like you can achieve as low as 2 VDS. This is the best thing we could have tried. Even with depleted mode transistors, we could have achieved only this one. So that is the thing, but we are more greedy and we want to have better current source whose Z-out is more valued and having lesser and lesser V min. So in that case, we can do one thing. There is another technique called gain boosting technique. We are going to talk about it. And whatever we want to do, make sure that we do not want to reduce the bandwidth. If you remember, when we started the cascode, we also started from here that how to improve gain. How to improve gain. So we listed down following things. Improve R out, increase it. How to increase R out? You can cascade the stages, right? If you're cascading or multi-stage, it's going to give you more and more gain, more and more required R out. Everything is improving, but that is going to reduce the bandwidth. If you want to see one example, let's assume that this is the circuit. What is the bandwidth of this one? 1 by 2 pi RC, right? Or you can say that there is a pole right, and V out by V in. You agree with this one, right? If I am going to add one more stage over here, what's going to happen? Let's assume that in between there is one voltage follower I kept with the gain of 1. What is V out? If this is V out 1. If this is R2, let's assume that both are same, exactly same. What is the next bandwidth? What is V out by V in? Find out and tell me. What you got? Santosh.
So bandwidth will be same, but slope will be more. Slope decade, that will be 40 kb per decade. Bandwidth will be same.
Okay. You agree with this one or no? There are two poles. Right? Can you write down the transfer function first and then find out? And draw the Bode plot. Once you got this, Srishti got the answer? Abhishek? Very simple, no?
Transfer function.
Okay, tell me what is transfer?
1 plus G omega RC.
G omega RC, okay. Then you can draw this one. Already Santosh has given the correct answer. You agree with this one? If both the poles are at the same place, one was giving minus 20 dB per decade, another is giving minus 40 dB per decade. Can you see? The bandwidth is getting reduced, right? We don't want that. Every stage is going to give you at least one pole, let's say. This is the best case. Generally, another one will be like, somewhere here, then will be somewhere like this. It depends where you're keeping. Generally, second pole is little bit higher than the first one, right? From the second stage, I mean to say. So, if you are adding the stages, it's going to reduce the bandwidth. We do not want that. We want something which is going to give you improved R out with the same bandwidth. That is only possible with the cascode. But we already did this. Cascode is giving you very high R out, and bandwidth is also same. It's not changing as you are getting with the single transistor. So that is what we are doing. But we want to having more thing where we are going to implement something called gain boosting technique as written over here, and we want to have R out as high as possible with or without decreasing the bandwidth. This is what we want. So let's assume that we are keeping same cascode thing, but the second particular transistor is actually biased by one stage of maybe common source amplifier or common gate or whatever you like. You just keep it over here, and then you are keeping your transistor. This technique is actually the gain boosting technique. What's going to happen over here is actually the impedance is getting multiplied. If you look at that, the gate current actually VGS was earlier like this, right? That is what there in your small signal model, right? So here actually you are improving the impedance by multiplying the same. So if the gain of this particular stage is GMA times ROA, A stands for amplifier, and just maybe I'm keeping one transistor also whose intrinsic gain is GMRO, right? That is getting multiplied with this gate, right? So if that is the case, can you tell me what is the R out? Just find out and let me know. Are you following what I'm saying? What I'm doing? So the technique I am doing is this source potential is actually getting multiplied with some amplifier. I'm keeping here in the loop, and that is what actually tuning the gate voltage of M2 means. It's actually improving VGS overall, right? So if that is the case, if you are looking into this with the small signal model where gate is here and this is here, so earlier it was just VGS. Now actually this got multiplied with GMA-RO gate, the gate to source voltage. By looking at that, can you tell me what should be the resistance from looking from here? Here it's RO1, there is no doubt. From here to here, what should be the resistance? So it's actually multiplied with the same quantity. So earlier it was GM to RO2 times RO1. Let's say I'm keeping RO1 at the end. But it's multiplied with another quantity which is adding at the input side, GMA ROA. Right. You solve it, you will find out that gate potential is actually increasing and it becomes GMA ROA. If this is around 20, this is around 20, and this is around 1 kilo, you can see almost like 400 kilo of gain you are seeing, right? So that is what this technique is known as the gain boosting, where you are keeping one amplifier. It might be common source amplifier, it might be common gate amplifier, or whatever you like, you can keep it over there, right? So that is how you can design it over here, and that is how you can improve the R out and at the same time, what will be the VDS? Okay. By the way, this will be the circuit, right? In that case, current as load. I'm keeping this GMA ROA, right? Any problem in this one? Abhishek Narmit. Now, no problem. What's her name? Shashank. Yeah, Shashank. Are you following or you are not writing anything? That's why I asked. If you are understanding, then there is no problem. So now, can you find out the required voltage also? Right? You can find out the voltage because R out we found out. By the way, okay, there is another name also of this circuit. It's known as regulated cascode current mirror. Through the gain boosting technique, you have made another current mirror whose name is regulated cascode current mirror. This is very much useful to achieving very high gain. Santosh, to achieve very high gain, this is the only technique available. Only technique if you want to have more than 60-70 dB of gain in an op amp which has been given to you, in which you have not designed. That is through gain boosting.
I am using this.
So then you have to use it, right? But when you are designing it, there is small trick which is not actually seen over here. But if the bandwidth of this system, let's say M1, M2, and whatever is on the path, if the bandwidth is, let's say 1 gigahertz, let's assume that if I want to design everything for 1 giga, this also have to be, all the poles and zeros has to be much higher than 1 giga, just to run the system very smoothly. Otherwise, these poles and zeros will be inside poles and zeros of M1 and M2. We'll study that. Don't worry. Then we are going to study, the design of op-amp and design of compensation and all these techniques. Little bit of control theory is required over there. Okay. So this is the thing. Okay. I'm not going into what will be the V out. I'm keeping to you people what will be the V out. You just find out. Okay. So I'm not solving it. You just solve on your own and you find out. Make sure that both the transistor has to be in saturation. The meaning of that one is both of them has to be at least VDS and VDS is more than 250 millivolt, right? Okay. Other than that, like I'm more greedy. I want to improve maybe higher and higher gain. So if you look at some of the probes which has almost like, have you heard about active probes? Have you seen active probes? Right? What is there inside active probes, in your opinion? What is the difference between passive probe and active probes? True. So inside that probe, there has to be, one box you are going to add, which is actually amplifier. But this amplifier does not amplify the signal. It is not for amplifying signal. It is amplifying for the impedance. If you remember, we wanted to have better and better impedance. If you remember 1x, 10x, we talked about it, right? 1000x. I also told if it is 10 raised to 5x, as it's increasing, the price is increasing very, very high, right? So there are like some of the company, one of the companies like Keysight, whose earlier name was Agilent. Now it's Keysight. They are designing, these probes, and they are very expensive as it is increasing the, its impedance, right? So if you want 10 raised to 5x, how to achieve 10 raised to 5x? Somebody can give me answer. How to achieve very high gain?
Multiple repeaters. Multiple this.
If you are adding multiple things, then it will decrease the bandwidth. Look, the whole game is with the fact that I do not want to decrease the bandwidth. Look, these probes can, work at very high frequency. If you have seen like SMA connectors are there. There is one thing is BNC. BNC is working easily with gigahertz, right? 1 or 2 gigahertz, no problem. SMA is much higher than that. SMA, SMB, SMC, the sub miniature, which is golden colored. If you have seen that connector, golden color, this one is aluminum colored or steel colored, right? So that BNC has lower impedance or the lower bandwidth. Sorry, I should not say lower impedance, but lower bandwidth. SMA has very high bandwidth. So I do not want to decrease the bandwidth with this particular feature. I want to have higher and higher bandwidth at higher impedance. So how to achieve higher impedance? What is your answer? How to achieve higher and higher impedance? Hmm? So one option is use cascode inside it. Second option, gain boosting, right? Add big circuitry, uh, and at the tip actually there are JFETs are used in this particular probe design, so that it gets little bit heated up and then it's used. But active probes are, that's a big market. Big market is there. If you can design just active probe, then it's like entire world will thank you, because there are very few companies who are designing very high bandwidth based, very high impedance based probes. So as I told you, like, this is going to give you GMRO is only going to give you the gain of around 20 volt per volt, which is just 26 dB. I don't want that much only. The If you remember, somewhere I wrote 400 kilo. I don't like 400 kilo. 400 kilo of resistance. The uh, the oscilloscope or the DSO which we are using in our laboratory, whose input impedance is 1 mega. We have to match that 1 mega. If here itself 400 kilo, and 1 mega is actually not so much useful, right? So you have to have higher and higher impedance. So how to achieve higher impedance? So the answer is not only this one. Big op amp, keep one circuit whose gain is very high. Earlier you got just 20 volt per volt. Keep something whose gain is 1000 volt per volt, or 3000 volt per volt, or much higher than what is there, right? 1000 is, by the way, 60 dB. So almost like, I'm talking about 100 dB of gain, or more and more, so that you can achieve the required impedance, because some application you want impedance at higher bandwidth, and this bandwidth is as high as something like 20 gigahertz, 30 gigahertz, or even more than that, where transmission line is the application, right? So there you require such kind of setup, or the regulated cascode current mirroring technique is required, and this is truly used. All active probes has actually this thing inside it, right? Of course you need to make this triangle also. We'll study that anyway. So slowly we are moving towards that. So if this is the circuit, this is very popular circuit. People are also used in circuit called LDO. You heard about LDO? There is one more BGR before LDO, right? It is called band gap reference, but LDO, it's called low dropout circuit, right? It is also like kind of voltage regulator, or you can say that linear regulator. All these things you must have heard, right, in your different courses in power electronics or many other places, right? So what exactly this LDO does is as follow. I want my main agenda is, I want not only I'm interested in output as current, I'm also interested in voltage also as output. I do not want any one of them getting reduced. It's all about the power. It's not about just voltage, not just about current. Sometimes you are seeing that voltage is coming or current is coming, but it's not a full picture. Full picture is power. How much is the power, right? So I do not want to change voltage for any load. So, or it can drive the current for a given voltage. This is what I want at the output. So if you look at this circuit, you can see that if this is V in over here, what is the voltage over here? Voltage O has to be V in only, right? V in does not change for a given current, because here it's a current mirror, it's getting mirrored. If it is n times this M1, so n times Iref is flowing through this particular transistor without having any problem, because of course whatever the rules you are following for this op amp, you have to follow that. What are the rules for this op amp?
Internal current.
Input impedance has to be infinity, output impedance has to be 0. What else? Rin has to be infinity, right? All these things you have to follow, and gain is infinite. These are the, what do you call it, ideal op amp, right? So ideal op amp, if it is following this, but understand there is no op amp or no circuit exist in this world which is going to have infinity 0. You have to just define it, what is infinity, right? It depending on the circuit, as I told you. Anything beyond 1 kilo, most of the time it's high. But some people, if you go to the probe design company like Keysight, might be saying 1 kilo is low, right? For them it's like anything beyond 1 mega is a really good impedance. So it depends. So you have to define it according to your need and your requirement, right? So maybe further things we are going to talk maybe next time, right, after the exam. Okay, I hope you are able to follow, right? Again we are going to talk about it.